Welcome everybody to the 7th talk of the Virtual Exchange seminars in Quantum Mobile Networks. As usual, I would like to ask the audience if there is any question regarding last week's presentation. Okay, so the students who need the ECTS can see, as usual in the chat, a link to the evaluation sheet for today's talk and a link to the exercises that are due as usual by the deadline. So today's talk is titled Age of Information in Quantum Mobile Networks and will be presented by Matheus Moraes de Brito from the Federal University of Pará, Brazil, Bruno Santos Martins, Camilo Henrique Martins dos Santos, still from the Federal University of Pará, Brazil, and by Oleksandr Pertsiukh from the University of Bern, Switzerland. As usual, the duration of the talk will be roughly 30 minutes, and after we will take 10 to 15 minutes for a question and answer session. As usual, you can either type your questions in the chat or you can directly ask them to the presenters at the end of their talk. So the first presenter can start his presentation.
Okay, everyone can see my screen?
Yeah.
So to start my presentation, I'm Matheus Brito and I'm from Federal University of Pará, and I'm going to present together with Oleksandr from University of Bern. So we are going to talk about the age of information applied to quantum networks. In a little agenda about our presentation, we will start with the introduction, and then we'll pass to the classical age of information, and then to the quantum multi-hop networks that is directly connected. And then I will pass my speech to Oleksandr. Then he will talk about the conceptual difference between them and some simulation. So to the introduction, where we consider the age of information as a metric, and it will show and we will return the freshness of the information and how it will propagate through the network. And we will deal especially with the time elapsed since the generation of the packet mostly recently delivered to the destination. So in some application, it can be considered as the closest to the real-time application, and lots of application with the time-sensitive data. So some areas that we can apply it is the IoT system, the fog cloud computing, and the video streaming. So some the authors of the reference talk about some scheduling algorithms and some protocols to optimize these transmissions, always using and managing the all resource network can provide, and to mitigate the factors that it can cause some congestion in the transmission. So our goal remains in exploring this latest solution in age of information applied to quantum mobile networks, of course, in talking about the classical age of information that is based on this to create to apply the methods in the quantum mobile networks. Then we'll discuss the age of information through some simulation and also comparing, appointing all the differences. So in the classic age of information, it also was previously established. We keep the freshness of information through a destination perspective. So some system to be applied can be an industrial plant, a smart house, or even a modern autonomous car. So all of these systems have some sensors, and these sensors transmit a lot of information, always, sorry for the noise, always some about physical phenomena. Like in the car, we can have the pedestrian, we can have the the air pressure in the tires, and all this information can need to be received and not need to be discarded. So we consider these transmissions through channel unreliable or less channels. So the authors consider some policies to scheduling and maintaining this freshness since we have these channels limitations. Some greedy policies can consider it in some symmetric networks as networks without the disturbance, and the highest current age the package can receive is as considered the optimal. And it's different what we see in general networks, and the policies scheduling can attempt this age of information minimization with considering this reliable channel. And we can see in the graphic as the age of information rises is when the newest package sent is received. So this sample sequence is associated to the evolution of the age of information. It's what these methods will try to minimize. So the age of information is considered also in the case of application in ubiquitous networks and some portable devices as mobile networks. So these applications need to be timely as possible and don't have the tolerance to support any delay, and it relies on the time-sensitive information. So there are the limitations also are treated, the resource network limitations, and the age metric will use it to keep the status updated. So the smallest age to be achieved is if a new package is available when the second oldest, the latest, finish its service. So in this other reference, it treats about the dissemination of the information and considering a source and multiple destinations. So it talks about as gossiping or some epidemic algorithms. So these base stations send the information through multiple nodes, and these gossip models will maintain all the recent updates. And what we already talked, it will represent the latest copy of the information to have already seen. So the gossip models will deal with these the characteristics of the general networks when it's dealing with mobility or source inputs, always searching for the higher and the low ages. So when we talk about the age of information in quantum networks, there was some reference to talk about, but the greatest to talk about here is about the multi-hop networks. So when we're facing this quantum information science growth, the quantum teleportation will be used to achieve the quantum communication. And as we've seen before, the Bell pairs is considered to be the entangled states. When two quantum systems, as electron or the photon, share this non-local correlation. And the entanglement swapping will establish the entanglement between two distant nodes, always through intermediate nodes. And this can solve some long distance quantum teleportation and occasional losses in the quantum channel. So these quantum wireless networks always require new communication mechanisms, and the author will propose a scheme where he enables the quantum teleportation between two nodes, which do not share initially and in mutual entanglement. So these simultaneous Bell measurements will be implied to the intermediate nodes, where the measurement results and the Bell types will be sent to destination nodes. So in his application, the sequential entanglement swapping will send through the upstream node. So these can force the intermediate nodes to wait for the classical information. And this operation can cause a large delay and I don't know if I can say the redundancy and the need of a new communication channel. So the simultaneous swap will reduce the end-to-end delay, and the author notes that can be used to the wired and the hybrid quantum networks. So to talk about a more recent study in the quantum multi-hop network, this author considers the mesh topology applied to the quantum networks with the multi-hop teleportation, and it enables the quantum teleportation to be realized between two nodes without the direction quantum channel. So these simultaneous Bell measurements in the source will be the sender, and all the intermediate nodes will send the measurements as the destination node. And it will keep the information to be sent through all the mesh topology. And these mesh topology can handle with a large amount of traffic, and it enables the transmission to be distributed even when the connection is down in some of the nodes. And these simultaneous measurements can reduce the hop-by-hop communication delay, as we see. He didn't talk about assertively as the what transmission time it can be reduced, but is a scheme that can reduce the overall transmission time. After this related work contextualization, I can pass my speech to Oleksandr and he will talk more.
We are coming to a conceptual and practical part here. In order to make it more applied and actually more visual, we will relate to the current OC model, which is the most basic principal conception of networking, at least in the classic networks. And spoiler that we will come to the basically the same structure, but with some changes after we do the application of the quantum technologies to it. So it figures out that since most of the part that quantum technologies will modify are coming to the basic network structures, the most affected would be the physical data link, transport, and network layers, which makes sense since these layers do provide the links between devices, both between network devices and the end hosts. And in our case of fundamental change of ways we transmit these data, they will face the most changes. And application, presentation, and session layers, well, they will be affected to a certain degree. For example, like we can count an SSH or SSL protocols, which are protocols for encryption, as a application or session layers protocol. However, most of these protocols would be related solely for the work of the end nodes, and therefore they will not be affected whatsoever. To show some practical differentiations in approaches, I would like to present some of the code we have developed so far. We have just several easy sketches. We would like to present more of them, but there will not be enough time for doing that. So on the first glance, it doesn't make much of a difference. However, I would like to show the fundamental difference in a certain numbers algorithm. So pretty much everybody familiar with a classical algorithm of sorting, which makes iterations by simply going through the arrays and iterating numbers one by one, comparing the one that you had right now to the previous one, and then storing the results. With quantum technologies, at least with using a Q-skit, which use the same principles and the same methodology as we assume the quantum technologies will use, at least the same mathematical models. We see that in order to even begin the work, we need to set up the qubit arrays, and I would like to remind that qubits and bits are quite different structures in their roots. Then we have to create a loop to constantly loop the code until the swaps occur. We also will have to make another kind of indexation in order to establish a quantum circuit. So the quantum technologies would actually come in handy. Therefore, you can see that differentiations in the approach is quite fundamental, and this will be very important in the second part of this section. Another crucial example of the differentiations and conceptual differences would be trial division and Shor's algorithm, which are obviously two different methods to approach the same problem of factoring large numbers, or simply put, in trial division, I would like to remind to everyone, we are attempting to find a primary factors of a number by sequentially testing each number. And in Shor's algorithm, we use a Fourier transforms, or in sometimes fast Fourier transforms, and quantum operations to compute the periodicity of an input and determine its factors, which is obviously much more efficient and faster way, although it does have a certain pretty much higher error rate, at least from technologies we have right now. Here is an example of how would we make a simple trial division algorithm and a Shor's algorithm implemented. So then again, unlike the classical methods, we need to initialize the circuit and work with it mostly during the whole algorithm. So that is a pretty key thing to remember for the second part. There are a lot of consequences in this shift of technology stacks that are rarely considered, and I would like to get to them right now, as we have seen the actual factual differences between the coding, as an example. So the fact to consider is that computational power of a quantum computer increases exponentially with the number of qubits, and also that will have a higher error rate than in any classical computer, which also means that requirements for the software and hardware modification will increase in order to keep the Colossus running intelligently and as expected. Now we're getting to a social part and how it will actually affect the social and economic structure. Not only quantum technologies could enable new types of digital infrastructure, which will obviously in turn require a new industry and specialists, but it will also reshape the society's perception and the way of thinking. One of the biggest currently available to foresee negative consequence of the quantum age is the risk of quantum computing becoming a monopoly due to the high costs and several other factors such as the scale and the needed temperature and other physical parameters needed to simply maintain the thing running. So as quantum computing technologies become increasingly more powerful and complex, only a few big companies may be able to afford them, which in turn could lead to a massive economic inequality and limit their access to advanced technologies for all others who do not have enough resources to maintain it. From that point on, it is only a question of time when the potential risk of quantum computing making cyber attacks more difficult to defend against becomes a reality. And then the key principle of security I would like to remind is that the security of a system always defined by security of its key. All the other layers we are putting upon it are non-essential compared to this first fundamental principle. And I put a graphics to just show how deep it actually gets. Quantum calculational possibilities, as it's well known, make the current tactics and strategies to create as secrets, like the keys for these systems, pretty vulnerable and obtainable through a pretty simple and short time calculations, which fundamentally shakes all the perceptions of the security that currently we do have. So getting to the conclusions. Yeah, before I get to them, I would like to also mention that I did not like we didn't put the facts of a tactical value, but only a strategical one. So, for example, we didn't put on the environmental influence, since strategically in any kind of observable future, we do not see how it can strategically impact on environment, since it would require quite a lot of quantum computers to actually create any sort of global warming or global adjustment to a planet climate whatsoever. So considering that we are only taking a look at the fundamentals and the strategic things that are going to happen in this age of quantum, we can say that generally OSI model will be almost unaffected in theory, having the same 7 layers, but these layers will be affected quite a lot. Application and presentation layer will remain all the same, and due to the simple fact that these layers are responsible for communication between nodes, and they are remaining unaffected by quantum. Well, mostly session and data layers will be simply adapted to encode data using qubits, while transport layer will be modified to account for these advanced data formats, and network layer will utilize entanglement-based protocols. Physical and data link layers will be adjusted to facilitate quantum computing operations, and in this part, physical layer will be like the most affected one. A new generation of professionals and a new redistribution of IT specialists is about to emerge, simply due to the fact that there will be different principles that are necessary to operate the quantum technologies, and they are certainly about to become of an important and massive meaning in a society. With quantum age comes new socio-economic impacts that are extremely hard to precisely prognose. And even in the age of information in quantum networks, the collaboration between classical computers and infrastructures will remain of a crucial importance. Also, not only it brings some positive moments, but also new threats are emerging as well.
So let's pass to the question and answer session. So we can start from the audience. Does anybody have a question?
I was just wondering, in terms of the age of information in quantum networks, I think the first paper that Matheus has presented talks about how to do simultaneous entanglement swapping instead of doing sequential entanglement swapping. This is something that I think I understand that. Just correct me if it's just I'm wrong. And I think that it does have an impact in the delay of the network. If you do simultaneous swapping, you don't have to wait until all the entanglements are completed, and you can perform faster transmission. I didn't understand how that actually relates to the information, age of information. Can you elaborate more on that? And thank you.
So the author in the first reference, it talks about it. You are correct. He deals with the sequential, and the sequential has way of working. So what the author proposes is the non-sequential. I think it can prepare all the intermediate nodes to know what the type of bell pair it will face. And it will, he discuss about the delay that he will mitigate, and not quite the age of information metric. So he considered that it will prevent the delay, but the sequential has more delay than the in general networks. So when you deal the age of information, I show you some classical networks, and they deal with some scheduling policies and so on. So these scheduling policies applied to quantum networks will be in some of what it can preserve these communications between the nodes to keep the last update of the information more near to the second oldest. I don't know if it answers your question.
Yeah, I was just wondering what kind of information. So it's the information about the entanglement state, the fidelity that will age during, I mean, like if I'm trying to do routing and somehow that information doesn't work anymore because it's a dynamic network, this is kind of the information that they are trying to avoid that to be like to age itself. What kind of information? Something like that.
So he deals with the classical information, and then the quantum. You mean like what is needed to settle the communication, the quantum communication. So he does not. He retire the classical information channel. It will be used as long with the quantum communication. It was he put in the paper. But if it has some application in the routing and it can affect the transmission of a package of certain information, not the about the communication, the author did not talk about this in the paper.
Thank you. Thank you.
Okay, more question. I think Antonio had one.
Yes, well, congratulations for your presentation. And my question is, in the proposal of mesh topology, they consider some kind of routing protocol or not in this paper?
The mesh topology applied to quantum networks, it does not be specific in the protocol. It brings a new mechanism to apply the quantum networks based on the mesh topology. So the mesh topology will deal with some losses or some disabling intermediate nodes. I mean, the protocols was a part that I did not focus when I'm bringing the quantum part.
Oh,
If I may add a little one to that answer, it is generally speaks about the principle of working with the methodology and not the exact technical protocols to be used. So it mostly describes the physical part and not the theoretical physical part and not the engineering part.
Okay, I see. Okay, thank you.
Yes, more questions? Okay, maybe I can ask one. Let's see. So in the age of information, the main goal that we want to achieve is that the delay between the moment where some information is generated at the source should be somehow minimized, so the time that it reaches the destination, especially if we have several pieces of information that are produced consecutively, then we assume that they try to get transmitted to the destination over several hops, and then maybe they can be lost. For example, if we have a very high transmission rate, or for example, if we want to minimize for example, the interference or somehow the loss, we want to reduce, for example, the speed of transmission. So that is basically all about finding the optimal rate of update to minimize the staleness of the information at the receiver. Okay, so this is just for the age of information part. Then there is the quantum aspect to it. So where do you see overlaps? Maybe this to Alex. Where do you see the overlap between exactly the quantum technology and this minimization of the transferring of the information?
Thank you, Antonio, for this question. That is actually a really good one. Since one of the real priorities in quantum technologies at least as it states right now, is also to know where exactly do we put our quantum channels. So since we have a very limited resources of even potentially of quantum computing and quantum channels, the separate task before we even proceed would be to identify the places where like the most effective places where should the quantum channels be stationed upon. I mean logistically, not even physically. So yes, obviously we do need a solution that will include both the fact that we want a faster communication, but also the fact that we have a very limited resources to work with. If that answers the question.
Yes, somehow. I'm more interested in knowing, for example, if you were designing such a network, and which characteristics of these networks would you consider to fine-tune how frequently you want to update information from the source and destination?
Well, yeah, obviously that would hugely and mostly depend on the type of the network and also on the importance of this network. So I guess the very first real usages of such devices and such networks would be for like federal data channels and for like messaging between a governmental or big corporate structures, stuff like that. And we will have also the maybe even some federal storages backups and that type of crucial networks. So naturally, we are talking about at least like thousands of terabytes flow per second.
That's still partially what I want to hear. Is I just want to hear, for example, you want to send a new qubit every 1 millisecond, every 10 milliseconds. How do you pick this number? What would be your strategy? Or every 1 microsecond? So which are the time scales we are talking, and on what parameters of your system does this number depend on?
Well, it hugely depends on our quantum channel and the number of entangled particles we have. Also, it hugely depends on a protocol we are using. So, like, if we will talk about QKD, like quantum key distribution, we will have a certain number, like initial number of data being exchanged, but after we actually have established this secure communication, it's pretty much like in classics with Diffie-Hellman protocols. Since we have exchanged those keys, they have been generated, and we now, the both parties understand each other. Yeah, from then it hugely depends only on the amount of information both correspondents produce. So yeah, we have like 3 main parameters: the quantum channel, the number of entangled particles, and actually the protocol, the purpose we are using this channel for.
Okay. Let's see. Is there any more question from the audience? Okay, maybe I can ask one to Matheus. Regarding the for example, the rate of contacts between nodes. And let's say that you have some mobile network. So let's say this multi-hop network is like a MANET, and you have nodes moving around. So you can have somehow different set of neighbors at every time. Did you have the chance of seeing how this impacts the age of information?
Applied to quantum networks,
Mm-hmm.
the multi-hop schemes that I presented in the papers did not consider the mobility and the source inputs as well as the papers in the classical. So when you deal with the mobility aspect and how it will affect, of course, it has a different status, a difference, characteristics about what will be transmitted, will come, and what will return. So these metrics will be applied in the future. I think it was applied in some quantum network studies, but in the reference that we took, we did not consider it. It's somehow can be more specific about these aspects, but I preferred some papers that deals with how the nodes will work in the entanglement swapping. So all these two reference, it considers more of a static network. I think I don't know if it will respond to your question.
Yeah, sure. So there wasn't so much aspects of mobility in the papers that you reviewed. Mm-hmm. Okay. So any question from the audience? Okay. So I guess if there is no further question, we can end the session a little bit earlier. So thanks to the speakers for joining in today. And as usual, we will meet next week, so on Friday, with the last talk of the series. All right. So again, if there is nothing else from your side, then thank you for joining today, and I will see you next week.